So the plan for today is I'm going to go over the third and fourth week by reviewing the quizzes for those weeks. That covers most of the materials, and that'll give us a starting point. I'm going to be diverging a little bit in case there's maybe things that I think might possibly be on the test that aren't necessarily in these homeworks. So we may not follow it exactly, but I think that's probably a good outline, good way to approach this. Okay, so I'm going to start with question one. Complete the conditional proportion table and use it to solve the problem. Most patients will undergo surgery, make routine recoveries, and discharge is planned, but some patients experience complications and their discharge is delayed. James had a large hospital and large and a small hospital, each performing major and minor surgeries. Data is collected at each hospital to see how many surgical patients have their discharges delayed. The results are shown in the table. Okay, so let's take a look. Again, this is a crosstab or a contingency table, or in this case, they call it a contingency proportion table because they don't actually just put in the number of people involved, but they put in a proportion, like 70 of 700. That means 10% of the large hospitals had delays after major surgery, and 15 out of 60 of the small hospitals. So this is 10%, and this is 25%, for instance. So it's not really, gotta be a little bit careful. It's not really just simply a number where you would just add across to get the total number of surgeries or something like that. Okay, or you could, in a sense, you could say the overall average for both was 70 and 15, 85 over 760. But you got a little bit careful about it because it's not our usual simple contingency table. It's a contingency proportional table. Overall, for what percentage surgical patients was discharge delayed? Okay, so anybody want to take a guess at how we're going to approach that? Okay, let's see. Yeah, every once in a while, I'm going to, as you join, I'm going to glance over. We got about 7 people on here now. I'm going to glance over and just going to make sure everybody's muted so we don't get much background noise. I got my sound turned down, so I won't hear it. If you guys hear some background noise, you'll have to, alert me to it so that I can make sure everybody's muted. Or you can just remind whoever signed on to mute. Okay, so let's take a look at this. Over what percentage of surgical patients was discharge delayed? Well, how many surgical patients did we have here? We had 700 major large hospital. We had 200 minor surgeries in large hospitals. So we had 900 surgeries here. We had 60 and 300 for a small hospital. So we had 700, 200, 900, 1200, 1260. And out of that 1260, I'm going to get my calculator out. Out of that 1260, how many were delayed? Well, 84, and well, I'm going to add them up here. 84 plus the plus it looks like 39 if I add those together, and I'm going to divide by my 1260. Okay, so the proportion that were delayed looks like about almost 10%, or about 9.7% of the surgeries were delayed. Okay, I think that's okay. I don't have the answer handy, I don't think. Let me see. I'll get something out here. Give me an idea. I'm pretty sure that's right. Okay, so you guys feel free to bump me if you think I'm making a mistake or something like that. Sometimes it's easy for me to, as I'm chatting away here, to overlook something. So just be a little bit careful. Remember, this was proportions here, not just strictly numbers. Okay, numbers are going to be a lot simpler, I think. Complete the proportion table and use it to solve the problem. Partially completed conditional table gives the relative frequencies of the data on age and years and sex for the residents of a retirement home. Okay, so let's see what we have here. According to this, 19% of the people in this retirement home are between 60 and 60, males between 60 and 69. 10%, 0.1, are between of the males are between 70 and 79, and 11% of the entire population is between over over 79. Okay, what percentage of the residents are males over 79? Okay, let's see. That seems pretty clear, doesn't it? I mean, let me see if there's a twist here that I don't know about. I don't think so, right? So I would say probably 11% or 0.11. Okay, so I would go for 11% there. Okay, I'm not sure why this is partially completed. Maybe next question will wake us up on that. The partially completed conditional proportional table again. Okay. What percentage of the residents are females in the age group 70 to 79? Females in the age group 70 to 79 is 20% or 0.2. Okay, seems pretty straightforward. And let's see, whoops, did I miss that there? Females 70, 79, 20%. There we go. Got it. Didn't take when I clicked. Okay. A group of volunteers for a clinical trial consists of, if I were going to make this a little bit more complicated, I might ask you to work out the totals here. So you know I might have asked you what percentage of residents in this home are male. Well, you just simply add up all the percentages at the top here to get the total for males. Total for females would be here going straight across. And of course, this should add up vertically to 1 if you got it correct. So we got 19 and 10 is 29, 39, 40% are males. So we got to have 60% down here, and 20, 20, and 20. That's 60% down here. Sure enough, it adds up that way. Similarly, you could add the columns and get the percentages. What percentage of residents were 60 to 69, and you'd fill in these various columns here, and that should also add up to 1. A group of volunteers, if you got a question, just go ahead and type it in there and interrupt me. A group of volunteers for a clinical trial consists of 81 women and 77 men. 18 of the women and 19 of the men have high blood pressure. If one of the volunteers is selected at random, find the probability that that person has high blood pressure, given that it is a woman. Okay, so we're only interested in the women, right? Correct? So if we're only interested in the women, it's a conditional probability, given that they're women. Okay, the trial had 81 women in it, right? And 18 of the women had high blood pressure. So really, right off the bat, I could probably say to myself, well, the proportion of women that have high blood pressure is 18 out of 81, 18 divided by 81. And if I want to, this might be a good time to maybe practice this. And maybe what I want to do is, I'm just going to close this up here. Whoops. I'm going to draw a contingency table. I think it might be good practice to do this, just for the hell of it. Okay, so I'm going to draw a contingency table for this distribution. Whoops. They don't ask you to, but I think it's a good idea to get some practice with this. Okay, so it's 2 by 2. We have 2 exposures. I'm going to call the gender the exposures. Male and female. And we have 2 outcomes in the columns, which would be high blood pressure. And they don't have high blood pressure. So how many males? Let's see, there's 81 women in this clinical trial. So this total is 81. There are so 81 women, 77 men, right? And 18 of the women have high blood pressure. So these are the women with high blood pressure, and 19 of the men have high blood pressure. Okay, so I actually, if I'm only interested in the proportion of women that have high blood pressure, I have what I need here, 18 over 81 women, right? Because I'm only interested in the women. Now, if I want to fill the rest of this in, obviously, if there's 19 out of 77 males don't have high blood pressure, then let's see, 58 males don't have high blood pressure. 18, let's see, 20, this would be 61, 63 females don't have high blood pressure. So now if I had asked you, given that the person has high blood pressure, what's the probability that they would be if I asked you what percentage of the population of this nursing home has high blood pressure? Well, then you have the capability now of adding up the 18 and 19 and getting 37, right? And seeing the total population and saying that that's 156, and saying 37 out of 56 is the overall prevalence of high blood pressure in this population. If I asked you, what's the probability of the person being a male, given that they have high blood pressure? Well, among the people that have high blood pressure, right, which is only 37, that's my condition that I have to fill. Given that they have high blood pressure, the probability that they're male is 19 out of 37, right? Because our condition is, given that they're male, given that they have high blood pressure, in other words, they're within this group of 37, what's the probability that they are male, right? Only 19 out of those 37 are male. So if you actually draw the contingency table, it might actually make it a little bit more obvious to you in some cases. Okay, yes, there we go. Thank you. I got a couple of people keeping up with me and helping me fill this stuff in as I stutter my way through it. Thanks a lot, Isabel. Okay, so again, bump me, mention something if I'm going too far astray or if I'm losing you or something like that. Let me know, okay? Okay, let's see. Which one was that? Was this one? No, next one, I guess. Next one is number 6. The table below describes the smoking habits of let's see, a group of asthma sufferers. That's a bad idea, right? Asthma and smoking. Okay, so let's see. We got men, women. This is completely filled out this time. We have non-smokers, light smokers, and heavy smokers. So now this is a 2x3 contingency table, right? There's 2 variables in the rows, and there's 3 variables in the columns. Okay, so let's see what they're asking for. What's the probability that a woman is a non-smoker? Okay, so the first condition, the condition that we are starting with is that the person is a woman. And we want to know what's the probability that a woman is a non-smoker. So we're not interested in the men, we're only interested in the women. So the total number of women is 516. Right. So what's the probability that a person who's a woman in this group is a non-smoker? Well, there's 363 women who are non-smokers in this group, so it's 363 over 516. Okay, so let's just get that so we can answer that. Where'd my calculator go? Let's see, there it is. One thing about computers, boy, is that you would think they'd find a better way to do this because they're really cumbersome, calculators on computers. So 363, and often you'll see me a lot of times using Excel if I really have involved calculations, because it's just so much easier than doing this stuff, poking and prodding and stuff like that. Oops. 363 divided by 516. And among women with asthma, 70% are non-smokers. Okay, 70.03. Looks like it's that one right up there. Okay. Thanks again. Good. I'm glad you keep typing those in because it lets me know that you guys are following me, and then that I can move on. The table below describes the smoking habits of a group of asthma sufferers. Okay, we got. Okay. What's the probability that a light smoker is a woman? Now let's look at the contingency here. What's satisfied to begin with? What condition do we have on the that narrows this group down? What's the probability that a light smoker is a woman? So it's got to be light smokers. So we're only interested in the light smokers. There's 130 light smokers. What's the probability that person is a woman? Well, it's 65 women out of those 130. 65 women are in that group of 130. So it'd be 65 over 130 or 50%. Okay, 0.5. Okay, so yeah, good work. Okay, so everybody get that? The condition here that had to be satisfied first is that we're only looking at light smoke. Probability that a light smoker is a woman. If I had said and said, if I instead said, what's the probability that a woman is a light smoker? Then the primary condition is that it's a woman, right? Which means that we have 509 people that we're looking at, and the probability that they're a light smoker would have been 65 over 509. See how that reverses? Does that help, Carosella? Yes. Does that make it a little bit clearer? So you got to read. You got to kind of. It's called computers call the computer programmers when they write code, lines of instructions for the computer, and they want to go back over it, they kind of break it up into segments, like what part is of this instruction does this. And that's kind of like parsing. You also do that with grammar, right? Like when you break up a sentence, a noun, verb, it's called parsing. So you kind of really have to parse this and ask what are my conditions here? What's the primary condition? Well, here, probably that a light smoker is a woman. Well, primary condition that has to be a light smoker. That's all we're in. What's the probability that a light smoker is a woman? We're only interested in light smoker. What's the probability that a woman is a light smoker? Well, we're starting with the fact that they're a woman, and we want to know what percentage of them are light smokers. So you really have to kind of parse that sentence a little bit. Okay, so use table and blood type below and gender to show how the probability of person. Use the table below, blood type show how. Find a probability a person is male, given that their blood type is A. Set up the problem, but don't solve it. Use the table below to show the probability a person is male, given that their blood type is A. So in other words, the primary condition we're already narrowed down to is that their blood type has to be type A. So here is type A. People in this column are type A. So what's the probability that a person is male, given that their blood type is type A? Well, the total proportion that is male type A is the sum of 0.226 and 0.177. So I need those two in the bottom of my equation, right? So it's the only one that's got them in the bottom of my fraction, right? My ratio. All the rest of them don't have it. So you could literally just check that off now and know that you're correct. But if you take a little bit closer, just to make sure, okay, the probability that a person is male given that blood type is A, well, the sum of these two would satisfy that, but only 0.177 of those is male, so that would be in the top of our ratio. So 0.17, and indeed, that's the only one that satisfies that. Okay, a little bit tricky, but if you take your time and figure it out, and the key here is figuring out what condition is already set. And in this case, the condition that's already set is that you're only looking at people that have, given that, you're only looking at people that have a blood type of A. For a particular test, the sensitivity and specificity reported was 0.96 and 0.93. Suppose that the prevalence rate of using a specific drug was actually 0.03. Calculate the probability that the individual is actually a drug user, given that the drug test is positive, right? Drug tests, all of a sudden, drug tests are in the news again because of tennis, right? So a lot of times you wonder, everyone, being clinicians, a lot of you guys wonder, like, these tests go off to the labs, and we know nothing's 100%. So you got to wonder a little bit about how accurate these tests are, what the likelihood that they would give a wrong answer either way. In other words, a positive test being wrong, or a negative test being wrong, or in our lingo, the positive predictive value. In other words, person gets a positive test, what the probability is that they really are a drug user, or negative predictive value. What's the probability that if they're negative, that they test negative, that they aren't using drugs? In other words, that they skated through the test. Okay, so there's a couple of ways that we could solve this. Okay, the primary way that I think this is intended in this question to be solved, since I see the information they gave you, is to use a formula, that really messy formula that we were working with. I want to do a couple of things here. I want to do this. I want to take a look at this more than one way. And I'm going to, let's see, sensitivity and specificity, okay. prevalence. Okay, I'm going to use this information. I'm going to first do this using this information to create a contingency table, a diagnostic table for this test. Okay, and you don't have to do this. This is kind of like not the most orthodox way to do this, but it kind of helps me a little bit. So I don't know if, it's kind of might be a way for you to understand these tables a little bit better. Okay, so what I'm going to do is first I'm going to set up a table. Okay, here's my table, and I of course got my two outputs and my inputs here. Okay, and I'm going to say to myself, I didn't draw that very well. I'm going to say to myself, okay, so now the exposure, let's see, the test would be, this is a test, positive test, right, or negative test, right? That's our diagnostic test, right? Another way, a lot of times I'll put D plus or D minus over here. I'm sorry, actually T plus. I don't want to use the D there, obviously, for you'll see why. What happened here? Oh, there we go. Well, I'm outside of the range of this. I'm going to start a new page here. Draw this a little bit better anyway. Okay, so this is my test plus. They tested positive, they tested negative, and this is they were using drugs or they were not using drugs. Okay, so first thing I'm going to do is these are going to be my totals here on the column on the bottom and across. Those are going to be my totals. So first thing I'm going to do is I'm going to look at the prevalence. The prevalence of using a specific drug was actually 0.033%. So I'm going to take a number. I'm going to make it a big number. I'm going to say a number like, say 10,000. That's a real big number, right? And I'm going to say to myself, okay, 3% of those people in this population use drugs. So how many people would I expect total out of 10,000 to be drug users? So that comes out to 300, right? 3% of 10,000 is 300. What percentage are not drug users? Well, it would be the difference, right? It would be 9,700, right, are not drug users. Okay, so now let's take a look at those 300 drug users. The sensitivity of my test, that describes how accurate the test is at detecting people that are using the drug. In other words, 96% of the time, it will correctly identify someone who's using the drug. So out of these 300 people, 96% of the time, it will correctly catch the person using the drug. 4% of the time, it's going to think that they're not using the drug. It's going to miss them. So 4% of 300 is 12 people. And 96% of 300 people, right, the sensitivity, how accurate it is going to be 988 people. I'm sorry, excuse me, 288 people. I got confused there with the 10,000. 288 people. Of course, this adds up to 300. I just did it backwards there because it made it easy. I could have just said, what's 96% of 300? And it turns out it's 288. Okay, everybody agree with those numbers? I'm not getting that wrong, right? Now, next, the sensitivity, the specificity rather, is how good it is at identifying negatives, how accurate it is with negatives. So it's 93% accurate on identifying negatives. Because I'm going to get my calculator up for this. So I have 9,700 people. Where is it? I got 9,700 people who are not drug users. And this is going to identify them correctly 93% of the time, times 0.93. Okay, the reason why I chose such a big number is I wanted to make sure that I didn't wind up with fractional people in here. It would still work fine, but it'd look a little funky. So 9,021 people. 9,021 people are correctly identified. They tested negative and they indeed don't use drugs. So now, how many people did it incorrectly identify? as drug users who don't use drugs. Well, it's going to be the difference between these two, right? Actually, I'll recalculate. What the hell? 9,700 times, it's going to be 7%. 0.07 is 679, right? And that adds up, right? I would think, I hope, 679. So if I add up across here, how many people total tested positive? Let's see, 7 carried a 1. Let's see, 15, 16. I'm not new math. 8, 967. And how many people tested negative total? And that's 9,033. And indeed, they add up to 10,000 also. Okay, have I lost anybody here? Right? You guys see how I constructed this table from this information that they gave us in question number 9. All I used was the specificity, the sensitivity, and the prevalence to construct this table. Okay, so now I chose 10,000. I could have chosen 1,000. The only problem, if I had chosen 1,000, I would have gotten 28.8 and 67.9. Still work fine. Still work just swell, but I just chose that big number, a big enough number that I wouldn't have to work with decimals. Okay, so now the question becomes, calculate the probability that an individual is a drug user given that the test is positive. In other words, a person tested positive, what's the probability that they actually use drugs? Well, it's 967 people tested positive, right? Okay, I'm going to write that down here. 967 people tested positive. Out of those 967 people, only 288 were drug users. Now, what is that called? That's called the positive predictive value. If you get a positive test, how likely is it that you really have that disease or are a drug user? So I get 288 divided by 288 divided by 967 equals about 29.8%. Right? Do we have a selection there that's 29.8%? 29.8%. There we go. 0.298. Kind of a little obvious, right? They added that extra decimal point at the end. Let me just. So now I'm going to repeat this using the formula. Okay, and the formula. Let's see what I have here. Let's see. Okay, so now let me see here. I'm going to repeat this using the formula and see if we get exactly the same answer. Because I need you guys to crush your fingers here because inevitably, the first time I try this, I always get it wrong. That's why I love doing this both ways. So I know when I get it to agree that I have the right answer. Okay, so let me dig up the formula here. I wrote down the formula, so I wouldn't have to remember it. You can write it down too because it's an open book test. Okay, so you guys remember that it's about 28%. Okay, so I'm going to write the formula out here. I'm going to write it out. I'm going to, rather than pasting it in as a picture, I'm going to actually write it out. So the formula is the sensitivity times the prevalence. The sensitivity times the prevalence divided by, see, what have we got on the bottom there? On the bottom there, we got the sensitivity times the prevalence again, right? And that's one thing. Plus, added to it separately, is 1 minus the specificity. 1 minus the specificity, right? And we're going to take that and multiply it by 1 minus the prevalence. Now, we got a lot of stuff to get. We have a lot of other stuff that we have to move on to. So I'm gonna mention this, but I'm not gonna try and show it in detail. But what's really happening here is the sensitivity times the prevalence. That 3% of the population has have the disease or are drug users. The sensitivity is 90, whatever it was, 96%. We're about to look that up, right? If I multiply 96% times a 0.03, it gives me the percentage of the population that tested positive, tested positive and actually have the disease, right? Now down here, sensitivity times the prevalence, number of people that tested positive and have the disease, as a proportion, that is, have the disease. And this over here is the number of people that tested positive that don't have the disease. In other words, the false positives. So this is the total correct positives over the total correct positives plus the wrong positives. In other words, just exactly what we did here with our table, except we're doing it here with proportions instead of directly using sensitivity and prevalence. Okay, so that's our positive predictive value. So let's calculate that. So sensitivity times the prevalence. Sensitivity was 0.96. 0.96 times 0.03, right? And on the bottom we have, which is the prevalence, we have the same thing, 0.96 times 0.03, right? Plus, now we got to make sure we add that separately, and we do these in correct order. 1 minus the specificity. Now the specificity was 93%, so that's going to be 0.07. 0.07 times 1 minus the prevalence. Now the prevalence was 7%, was 93, excuse me. The prevalence was 3%, so 1 minus the prevalence is 0.97%. Okay, everybody happy with those numbers? Okay, again, interrupt me if I get it wrong, because if I get this right the first time, it'll be the first time in about 8 semesters. Okay, I've been lucky this semester. I think there's something else that I had issues with that came up occasionally for me. Okay, let's see, 0.96. I'm going to do this in 3 steps. Times 0.03. Okay, comes out to be 0.0288. 0.0288. 0.0288 divided by, okay, now this is the same thing, right? 0.0288 plus, and let's figure out what this second part is. Oops, so I can't get to it here. And so we got 0.07 times 0.97. And that comes out to 0.0679. These numbers look familiar, by the way. 288, remember that 10,000? Remember I used a nice round number like 10,000, right? Kind of ironic, right? Because these numbers are just, since these are proportions, they're coming back as proportions instead of actual people. So 0.0769. What was that again? I forgot that already. Oh no, I forgot it. I cleared it out, I guess. Okay, let me try this again. 0.07 times 0.97. 679. Okay. 0.0679. Okay, so I add these up. 0.0288 over, and let me try and add these now. How many decimal places I have here? Here. So 9 is 7. 7 and 5 is 6. 1. 8 is 9. 0.09. I think I got that right. Okay, is that what let's see what I got for a final answer here. I got 2 answers showing up here. Press my fingers here. 0.0288 divided by 0.0967 equals 0.297, or about 29.8%, which was the same answer that we got before. which is a Christian miracle because, like I said, I never seem to get it right first time. However, by doing this both ways, I kind of nailed it down here. I know that I didn't miscalculate here, which is very easy to do, right? I know that I got the right answer because when I did it the other way, I got exactly the same answer. And it also, we learned a little bit about how this works and what this equation actually means, right? This is 288 people, this is 679 people, and this is 288 people on top. So we kind of see where this formula comes from and how it works. Okay, so I wish I could have worked it out a little bit, if I could have explained it a little bit better in terms of how this formula was created, and this whole idea of Bayes' theorem. We could have gone back over that a little bit more, but we're a little bit pressed for time. Okay, so last question in this session, in this quiz. Suppose that 3% of the people in a given community of adults have attempted suicide. Suppose it is known that 20% of the community are living below the poverty line. If these two events are independent, what is the probability that a person selected at random from the community will have attempted suicide and be living below the poverty line? Okay, so now when you have independent events, you can use the multiplication rule, right? Suppose that you got 3% of the population, right? Let's see, 3% of the population is has attempted suicide, and 20% of the population is below the poverty level. If there's no association between these two events, the answer would be just simply 0.3 times 0.03 times 0.2, which would be 0.06, right? Point, 0.00. Let me think about this. Extra decimal point, 0.03, 0.03, 0.006, right? Everybody agree with that answer? Right? It's the multiplication rule. The key here is that these two events are independent. In other words, let's say that 10% of a population has red hair, and 20% of the population is left-handed. What's the probability that a randomly selected person it will have both red hair and be left-handed? Well, there's no association that I know of between having red hair and being left-handed. So it's just the 10% for being a redhead times the 20% for being left-handed. So in that case, it would be 2% would be the probability of that person being both left-handed and being a redhead. Okay, now that's interesting because now listen, I could twist this if I were giving you a test now. I could twist this around and tell you that let's see, if I told you that 10% of people in a given community have diabetes, and 40% of that population is male. 10% have diabetes, 40% is male. And I tell you that the overall rate of diabetes in this population, the probability of picking a randomly selected male from this population, randomly selecting someone from this population and having them be male and diabetic is 7%. And I ask you, are these two variables independent? The answer to that would be no, because if 10% are diabetic and 40% are male, I would expect the probability of picking a random male out to be 10% times 40%, or in other words, 4%. But if I told you that the real probability is 7%, well, now something's wrong. That random probability of having both properties is too high. So they're not independent. For some reason, males are more likely than females to have, even though the whole overall population may be 10% diabetes, males appear to be more likely to have diabetes. So you can use this backwards as well. So keep an eye open for that on the test and see if that comes out. If the multiplication rule doesn't work, then you know the samples are not independent, or you know that those variables are not independent of each other. Okay, let's move on to the next one. Okay, it's going to scold me for not finishing that. Oh, it's going to completely scold me. I'm going to go back in. I have to go back in. Okay, quizzes. Okay, let's go on to the fourth week. How are we going on time? Not great on time, but we're going to. Okay, quiz 4. Okay. Survey of 1,500 American households found that 30% of the respondents have health insurance. Is this a parameter or a statistic? Okay, now remember, what's statistic? Statistic involves a sample. A parameter involves a population. 1,500 American households, 33. Well, that's a sample. That's not all American households. That's a sample of American households. So this is a statistic. Okay, and also the other thing that you might want to keep in mind is that usually parameters like the mean of a population is indicated as a Greek letter mu, for instance. Standard deviation is sigma, and if it's the mean and standard deviation of a sample, it's usually an Arabic or an English letter, whichever you want to call it, which is x bar, for instance, x with a bar over it, or just SD or something like that for standard deviation, or S. It is believed that the population mean total cholesterol 20 adults 20 years or older is 196. Is this value a parameter or a statistic? In this case, we're talking about a parameter because we're talking about the population mean. Infant mortality per 1,000 live births for 50 states and District of Columbia has a mean of 0.698 and a standard deviation of 1.62. Assuming that the distribution is normal, what percentage of infants of states have an infant mortality between 5.36 and 8.60 per 1,000 live births? Well, I'm hoping that this is going to be a little bit of a simple solve. It may not be. Okay, so let's take a look at this. I'm going to pull up a sheet of paper. And these numbers for these 50 states, they said were normally distributed, right? And this distribution had a mean of 6.98, right? And a standard deviation, right? Standard deviation of 1.62, right? Now, assuming that this is normal, what percentage of states have an infant mortality between 5.36? I'm just going to draw that anywhere, 5.36, and what's the other number? And 8.60. Okay, well, let's look at these differences. One of the ways that I can see what the percentages in this normal distribution are, as we've learned with the empirical formula, is to look at the not so much the number itself, but the number of standard deviations that number represents from the mean. So this number, I'm going to call that Z1. That number Z-scores, or number of standard deviations, is going to be X, the value, minus X bar or mu or X bar, over the standard deviation. Okay, so that number is going to be 5.36 minus 6.98 over the standard deviation, which is 1.62. Let's see if I got lucky here. Okay, 6.98, but if I subtract those two, it's going to come out to 2, 6, and 1. 1.62 over 1.62. Right, so this is negative 1 z-score, negative 1 standard deviation, and I'm going to hazard a guess here and say that 8.6 minus 6.98 is also going to be over 1.62 is also going to be equal to 1 as well. I'm pretty sure that's what the case is. So we know we're looking at the area between negative 1 standard deviation and positive 1 standard deviation. And we know that area is approximately 68%, right? I think it's 68.2, a little bit more accurately, but we know from the empirical formula it's going to be pretty close to that. So if these numbers were close enough together that there would be some doubt here, we'd have to go to the table. But there's really nothing that's really close to 68%, close enough to really challenge that answer. So I'm just going to put in 68%. Okay, everybody remember that standard normal distribution and our empirical rule, right? Our empirical rule is that in a normal distribution, approximately 68% of the results are between one standard deviation above and below. And if I go 2 standard deviations below and above, it's 95%. If I go 3 standard deviations above and below, it's not 99.7%, 0.997, for instance. Okay, good. So now let's move on to the next question. The lengths of human pregnancies are normally distributed with a mean of 288 days and a standard deviation of 15 days. Approximately what percentage of pregnancies last at least 298 days? So in other words, that's another way of saying 298 days or more, right? So we knowing that, we'll go in here, we'll make a little sketch. And again, always helps them. I mean, you could literally try and solve this easily without using a sketch. A lot of you probably are perfectly comfortable with that, right? But I think maybe I'll give it a try with a sketch. So here's our distribution. Our mean was 268, and our standard deviation was 15. Okay, so, and we want to know what's the percentage of pregnancies that last more than 298 days or longer? 298. So my z-score for 298 is going to be equal to 298x minus mu, 268, over 15, which is 30 over 15 is 2, right? So this is positive 2 is my z-score. So this is the area I'm interested in here. So I know that if I were to look at minus 2 to 2, this would be 95% of this distribution's population, right? 95% would be represented there. So since the normal distribution is symmetrical, that only leaves me 5% to be outside that range, above or below, right? So if it's symmetrical, same area down here is up here, then the area that's above 298 can only be 2.5%. Right, so let's see if we got a selection here, 2.5%. And sure enough, there we go, 2.5%. Okay, good. Let's go on to the next one. A nurse supervisor found that the staff nurses complete certain tasks in 10 minutes on average. If the times required to complete the task are approximately normally distributed with a standard deviation of 3, mean of 10, and standard deviation of 10, what percentage of nurses complete the task in less than 5 minutes? Okay, in other words, let's see. And they want that's just the way they want the answer so that it works out, right? Okay, so that it'll self-grade. So let's take a look at this. I'm going to, again, sketch this. Okay. Cursor go. There it goes. Right? A mean of 10. And a standard deviation, sigma equals 3. Okay. Percentage nurses complete the task in less than 5 minutes. This is 10. We're interested in 5. Right? So what's the z-score for 5? Let's see. Z is equal to 5 minus 10 over 3, right? That's my x minus my mean, is equal to 5 over 3 is equal to 1.6666, because you got to call it 1.67. Okay, so now I can't use I can kind of get an idea from my empirical formula, but it won't solve this problem for me. There's a couple of ways I could solve this problem. Okay, right, you're right, it's negative. Absolutely right. Thanks for pointing that out. Negative. Okay. I can use the Excel functions. In fact, let me do that right now. I'm going to use the Excel function. This one, I'm going to, for this one, I'm going to use Excel and the table, right? So you can see how I would do it both ways. But obviously, it's a little bit easier sometimes to use Excel because it's just there all the time. I'm going to load this up. I'm going to make it even bigger, 300%. Oh, yeah, even bigger than that, 400%. Okay, I don't know if this is going to help see it at all, but I'll give it a try. Okay, so I'm interested in what the percentage of that, what that area is compared to the rest of this distribution. And I know that the point that I'm going for is the area to the left, right? I want to know which of them compete. What is it more? Let me go back and read that. Less than 5 minutes. I know I want the area to the left because I'm interested in proportion of this distribution that's to the left of 5 minutes or less than 5 minutes. So we have a function called norm dist, right? I'm going to put, as soon as I put the parentheses in, I don't know if you can see it very well down here. You can, but it gives me a hint of what I can put in there. I can put in the mean, the value, the mean, the standard deviation, and cumulative, whether I not want the area or just the height of a line at that point, right? Well, that's one function I could use. There's another function I could use, which is norm dist, right? And that function only asks for the z-score, right? So I've already calculated the z-score, so I'm going to use that function, 1.67, okay? And it comes out to be 95 point, well, now I made a mistake there, didn't I? I just did the same thing. I went in there and I like a bull in a china shop, and I forgot to put the negative sign in there. And in fact, it's 1 minus what I just got, because that would have been the area from the all the way up as z-score plus 1.67 all the way to the left, right? So that my area is 4.704. Now, interestingly enough, what if I had used the other formula, norm dist instead of norm dist? Parentheses. Well, I could put in my x. My x was 5 minutes. My mean, which was 10, comma, my standard deviation, which was 3, and true or cumulative. Hit enter, and I get exactly the same answer. So I could have saved myself some calculation by using norm dist rather than norm dist. So either one of these functions is appropriate. It's just what your starting point is. In this one, your starting point, if you have your mean, your standard deviation, your the value you're interested in, just keep in mind this describes always the area to the left of that value. If I had put in a plus, if I had put in a plus over here, it would have been the area from here all the way to the left. So if I was interested in this area here, I would have to subtract the value I got from 1 to get the area that's left behind, right? So I'm sure it's going to come up in a second, isn't it? Okay, so let's go back here. Okay, let's see. A percentage of nurses is requiring more than 10 minutes to complete the task. Okay. A couple of ways I could do this. I could go double click back in here or in here. Oops. I'll double click back in here. And this time I'm going to put 10. It's going to take 10 minutes. The mean is 10 minutes. And standard deviation is 3. And to be honest with you, it's pretty obvious, isn't it? Because more than 10 minutes, well, remember, this is the area to the left. 10 is the mean. So half the nurse is going to take more than 10 minutes. Right? That should be pretty obvious, I think. Right? But in this case, since it's more than 10 minutes, we're actually taking that 0.05, which is the bottom half of the curve, and we're subtracting it from 1, just happens to be the same value. The probability a nurse who is just assigned the test will take between 8 and 12 minutes to complete it. So now we need to really find 2 areas here, don't we? A couple of ways we could do this. Now what we need to do, bring this up here, and let me erase some of this junk I wrote here. Okay, now we want to know how long it'll take for a new nurse to complete the task between 8 minutes and 12 minutes. So given the way that, first of all, right off the bat, I know that this isn't 7 and 13 would have been nice because then they would have been 1 standard deviation, 1 to the left. But this isn't. So there's a couple of ways I could do this. I need to figure this out. So one way I think I could do this is if I know what the area is from here down, right? I know I can use norm dist or norm dist to calculate that. And then I find the area from here down, right? All I need to do is take this bigger area, subtract the smaller area from it, and I'm left with the area in between. The percentage of nurses that would finish it between, new nurses that would finish it between 8 and 12 minutes. Okay, so let's give that a try here. Okay, so norm, and I'm going to do this. I'm going to save myself a little bit of time and effort by using the norm dist formula rather than norm sdist. So if I use norm sdist, the bigger value, remember the bigger one was 12 minutes, right? Average is 10, 3 is standard deviation, and true. So that area from that point to the left is 0.74. Okay, in the other area, norm dist, that's going to be 8 minutes, comma, 10-minute average, mean, 3-minute standard deviation, and true. Okay, and that's 25%. And the area that includes both of them. In other words, if I chop off that 25% from the 74%, which is the area between them, it's going to be equal to that minus this, which is a little less than 50% of the time the new nurses will get it done in that period of time. Are you guys okay with that? Does that make sense to you? Can I get a yes or a no there? Anybody struggling with that? Okay, good. I'm gonna do the last part of this, and then I'm gonna do one with the. I can go back and do one of these using the table. Okay, just so you can see how you would use the table for it. Maybe the one we just did. The slowest 20% are given additional training. What test time qualified nurses for? What is this? Oh, okay. If you're in the bottom 20%, you get extra training. So they're asking, before you got the extra training, how slow did you have to do it to be in the lowest 20%? Okay, let's look at our distribution again. If I can find it. There it is. Let's see. Let me get back to that page. I lose that page. Okay. Now this time, I'm going to back up on this. Oops. Oh, I know what happened here. Okay. Okay. I'm going to draw this again. Right. Okay, I'm just going to sketch it again. Whoops. Okay, why aren't we writing? Oh, wrong side. Okay. Okay, so the mean was 10, standard deviation was 3, and we want to know how slow you had to do it to be in the bottom 20%. In other words, what value here represents the amount of time that you would have to take to do the task if you were in the bottom 20%? Hang on a second here. The slowest 20%. You want to know something? Actually, it's not going to change the answer, but what they're really looking for is the slowest 20%, and the slowest 20% is up here, right? Because like this is 10 minutes, 12 minutes, so on and so forth. This is the amount of time it takes to get it done. So we're looking for what that value has to be in the slowest 20% of the nurses. Okay, so let's look at our formula there for z-score, right? So we want to know what the z-score for that is and convert that into an area. Okay, so now let's see. I need to know what the z-score is there, because then if I know the z-score, I can figure out what the rest of this is. Well, I need to have a way to change an area into a z-score. I have a way to change a z-score into an area, a z-score into an area, right? Calculate the percentage. Now I need a way to do the opposite. Okay, so I had this, let's see, norm s dist, norm s dist, right? That was very convenient because all I needed there was the z-score to get the area that was to the left of that z-score. I wish I had a way of doing the inverse of that, right? Well, let's see if maybe I do. Norm inverse. Okay, what is that going to add? Whoops, norm inverse. Wrong way. What is that going to ask me? Whoops, norm, is it norm S inverse? Norm S inverse, right? Norm inverse asked me for the z-score and gave me the area, Norm S inverse asks me for the probability, the area, and gives me the z-score. So I'm going to put in here the probability is, what is the probability to the left of this value? We want the slowest 20% or the 20% highest part of the curve. So really, we're going to give it the 80% to the left. It's 80% to the left. So we're always working to the left here. And that means that it has a z-score of 0.84, right? So that's going to be our z-score. So if I go back here and I say to myself, my z-score is 0.84, right? So let me see what I have here. My z-score is 0.8. Z is equal to x, the value that we're interested in. What is this value? Minus the mean over the standard deviation. So my z-score is 0.84 is equal to x minus 10 over the standard deviation, which is 3. So I can actually solve this equation, right? It's just a little bit algebra, times 3 on both sides. We got 3 times 0.84, right? And that's a minus 10, and that becomes a plus 10, right? Is equal to what x is equal to, right? So 3 times 0.84 is equal to 2.52 plus 10 is equal to 12.52. So in order to have 20% of the population to the right of this, you would have to have a value of 12.52. You could actually do this backwards now. You could say, hey, well, let me see what, if I got a z-score, if I got a value of 12.52, what would be the area that's left up here? I could actually do this now and check this. I can use norm dis. Right? Okay, what's x? X is 12.52, comma, the mean is 10, standard deviation is 3, cumulative is true. Let's see what that gives me now. It gives me 80% of the curve is to the left of that value, so we know we're right. We got the right answer. Okay, so there's a couple of ways that you could do this. Now, just to show you quickly, if I wanted to know what percentage of the curve, let me find Rusty. I think that's the quickest one I can get to. And it's very similar to the t-tables in your book. T-table. Here we go. If I were to do the same thing here, if I wanted to know what area of this, what the z-score is for a z-score of, let's say a z-score of plus 2.0, right? Well, I would go over here. See, notice all the z-scores are on the first page because they represent all areas that are to the left of the mean. So they're all going to be negative. And if I were looking for a z-score for negative 1.56, it'd be negative 1.5, 0, 1, 2, 3, 4, 5, 6. So the left of a z-score of a negative 1.56 would be an area of about 6%. Okay, to the left of an area, notice now we're on the right side of the mean, but now we're still talking about the area to the left. If I wanted to know what the area to the left of a z-score of 1.71 is 1.701. Well, 90.956% of the distribution is to the left of that value. Well, I want to know what's to the right of that value, that z-score. I would just subtract that from 1. It would be 0.04 or something. Okay, now let's just take a look at the problem we had here. In this problem, we wanted to know what is the z-score that represents 20% of the area is above that value, 80% of it is below that. So we're only interested in the area below it on these tables. So let's take a look at what z-score you would need in order to have a value of 20% above and 80% below. Okay, so let's look for 80%. So the closest value to 80% that I have is this one right here, which is plus 0.084. So my z-score is plus 0.084. Well, plus 0.084, that sounds familiar. Wasn't that the z-score that we came up with before? And in fact, let me just take my calculator. Plus 0.084, right? That would be my z-score, 0.08. Excuse me. My z-score would be 0.84, 0.84, right? Times my standard deviation, which is 3, would give me 2.52. So I know I'm to the right of the mean, which is 10. So my value would be 12.52 again. So we get the same answer that we would have gotten otherwise, except we get it with a table. Again, if you've got the time and you want to keep us there all night, I know some of you guys do when we give these tests, and you're interested in punishing us, and you maybe even going a little late, right? You can check yourself. You can look at this from different directions to make sure you get the same answer, and that you don't make any surprise. You don't surprise yourself with some inadvertent errors. Okay, so now let's go on to the next problem and see how we're doing here. We're running a little bit late, but that's okay. I don't like to keep you guys. I don't like to keep these too long because I really start to lose people after a while. It's really pretty tedious, especially when you cover a lot of stuff. According to New York City Department of Health and Hygiene, 28% of New Yorkers answered yes to this question. Have you been told by a doctor, blah, 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 that you have hypertension? In a group of 10 New Yorkers selected at random, what is the probability that exactly 2 of them have hypertension? Well, now we're dealing with something called the binomial distribution. Okay, and we know binomial distribution can be described in some cases as similar to a normal distribution. We're going to talk about that in a second. It's called normal approximation to the binomial distribution. But it has different properties because we're dealing with a selection where it's kind of like always heads and tails, right? It's always binomial, always 2 choices, diabetic, not diabetic, hypertensive, not hypertensive. So let's see. So in a group of 10 New Yorkers selected random, what's the probability exactly 2 of them are hypertensive? So I'm going to go over to Excel. I'm not going to go through as quite as much of a discussion about how we got to this point. There is a formula for this that involves combinatorials and factorials and so on and so forth, and natural logarithms and so on and so forth. Very complicated. So I'm just going to take a practical approach to this. How do we determine what the probability is that if I pick out 10 people at random, what's the probability that exactly 2 out of those 10? Okay, we know overall the probability is 28.3%. So I'm going to use something in Excel called Binomial Dist. I know that there's in most versions of Excel, a lot of times you'll come across stuff that says binom.dist, right? So you sort of came up there, or just binom dist. They're really the same function for the most part. I'm used to doing this old school, so I have a tendency of just using binom dist. Again, Excel helps us out, tells us what it's interested in. So it's interested in the number of successes. That means if you have a number of trials is the number of people that you picked at random, which is 10. Number of successes is the number of people that have that condition, which in this case is high blood pressure. And the probability in the population overall of success of having that condition, and whether it's cumulative or not. In this case, cumulative means something. It means something practical, unlike in the normal distribution. Okay, so the number of successes would be 2, comma, out of 10 people, and the probability is 0.283, 28.3%. And in this case, we want to know the probability for only 2 out of 10. We're not interested in probability for 1 out of 10, none out of 10, 5 out of 10. Exactly getting exactly this outcome. So in here, I type in for true, I type in for cumulative, I type in false, right? Because I just want that probability. And there it is. If it had been worded differently, and I wanted the probability for 2 or fewer. In other words, a success could have been 1, or a success could have been 0. Well, in that case, I would type in binom dist, and it's the same thing, right? It's 2, right? Number of successes, comma 10. Number of trials, number biggest 0.283. Except this time, I would say true, and it would give me a probability for not just 2, but all possibilities below it. 2 out of 10, 1 out of 10, 0 out of 10. Obviously, a lot more likely. Oops. I kind of messed up that formula. Let me see if I got it right this time. True. Yeah, that's what I want. So the probability is quite a bit more than it was before. Okay, so and that's the way that you would use this, right? Because then this is the probability left. Now, if I asked you, what's the probability of having more than 2 people out of 10, a selection 10 randomly selected people, more than 2 out of 10, it would be equal to 1 minus the probability for 2 or less. Now, what's the probability of having 2 or more? Well, 2 or more, right? This would not be right for 2 or more because this is only 3, 4, 5, 6, 7. It's 1 minus, this includes the 2 here. This doesn't. So if I ask you for the probability of having 2 or more, you would have to say binomial dist, parentheses, number of successes is 1, comma, 10, comma, 0.283, comma, true, and then take 1 minus that to get 2 or more. Tricky, right? It's a little bit tricky. So you got to read the question carefully and know exactly what this formula is giving you, right? Okay, so now what's the next part? What's the probability if you randomly selected 10 people from this population? At most, 2 individuals are hypertensive. So at most would mean 2, 1, or 0, which we've already calculated, right? So at most 2 would be 2, 1, or 0. So it's kind of like a word problem. What's the probability of randomly selected 10 individuals in the population? At least one of them will be hypertensive. So at least one would be 1, 2, 3, 4, everything but one. At least one would be everything but 0. So you could calculate equals norm. What's probability getting none? Oops. Binomial dist. Parentheses. 0, comma, 10, comma, 0.283, comma, true or false. Doesn't matter because 0 is going to be the same, true or false, because there's nothing to the left of it. Okay, so 3.5%, right? So that means 96.5% is going to be my answer. Is going to be equal to 1 minus that. Probability of getting everything except 0 for the outcome. Okay, so let's take a look at the next one. According to behavioral risk factors, 58% of Americans have a sedentary lifestyle. Suppose you select a sample of 12 individuals and find 10 of them do not exercise regularly. Assuming that the surveillance system is correct, what is the probability that you would have attained such a sample? Okay, so 58% of Americans have a sedentary lifestyle, so our probability is 0.58. You select a sample of 10 individuals, of 12 individuals, and 10 of them do not exercise properly. So what's the probability that you would have gotten? Now, just a little bit of interpretation here. Now, what's the probability? This could be 2 questions. Well, what's the probability that you would get at least exactly 10, right? Exactly. Let's see, where sample of 12 people, find problem that 10 of them do not exercise regularly. That could mean exactly 10 or 10 or more out of your sample of 12 do not exercise properly. I think that is probably they're looking for 10 or more. Right? So if they're looking for 10 or more, right, that means that the probability, we can't work that way. We've got to work down. So 10, 11, or 12 would satisfy this. So I want to know what's the probability of getting 9 or fewer, right? So the probability of getting 9 or fewer is going to be equal to binomial dist, parentheses, okay, and let's see what we got. We have 9, comma, out of a sample of 12, comma, the probability is 0.58, comma, true. And now I'm interested in only the part that's above that, 10, 11, or 12. 1 equals 1 minus this or that. And that's not multiple choice, so I can't answer that question. I'd have to go back to the answer sheet to make sure we're getting the right answer here. I don't know if I have that here. I'm pretty sure that we're doing this right. Just hang out for a second while I figure this out. Try and figure out whether or not we're... Okay. Okay. I'm gonna leave that at that because I'm not positive which direction here. But if the question, let me read this again. Suppose you need a sample of 12 and you find that 10 of them do not exercise. So what is the probability you will obtain such a sample? You know, if that were question, yeah, I'm not in love with this question. If that question, I might have phrased this question, what's the probability you would obtain exactly such a sample? I would have said, what's the probability of getting exactly 10? And the answer there would be binomial dist, right, comma, what's the probability of getting exactly 10, not 10 or more? 10, comma, 12, comma, 0.283, I think it was, and false. Because that'll give us a probability of getting exactly 10 out of 12 in this population, and it would be vanishingly small. It would be a very tiny number. So I'm not sure, you know, because the question is, I'm a little uncomfortable with the question. You know, the way I would have phrased it, I would have said, what's the probability that you would have gotten 10 or more out of 12? But it worded the way it is, it sounds like this would be the right answer. I'm kind of stretching it a little bit, I think. Right? What do you guys think? Did I put 9 instead of... You put 9 instead of 10. Not here, right? 10 is right here, right? Oh, did I do something else wrong here? Let me go back up here. 0.258. Okay. Yeah, and I put 9 here on purpose because that's going to give me the probability for 9 or fewer, which would then leave the probability, if I subtract it from 1, the probability for 10 or more, right? So that's why, and that's also vanishingly small, right? Because the probability of 11 or 12 is even smaller than the probability of 10, which is this tiny number. Yeah. Okay. Yeah. Thank you for pointing that out. The probability is 0.58 for what? You're pointing out that that's what I had put down rather than. I'm sorry. I'm thinking of the previous problem here. 0.58, and yeah, and over here, this is the one I did wrong. There you go. I completely went back to the other problem. 0.58. Right? That better? Okay. Yeah. Okay. That's 0.58. This was one that was. Oh yeah. Okay. Makes the problems up. Okay. But so, you know, if you read this literally, this would be the correct answer. If you used my interpretation, then this would be the right answer. Right? Not a big difference. This one includes the probability for 11 out of 12 and 12 out of 12. Okay. How likely is it to observe such a sample if 58%? How likely is it likely to observe such a sample if 58% of the is like? Well, I guess it's not unlikely, right? That's 5. I hate this question. I don't know. What's the answer to this? Would you consider 5% likely or unlikely, right? So I would say it's unlikely. It's less than 50% for sure, but I don't know how unlikely necessarily it would be. So I get one yes and one no. Yeah, that's why I'm not in love with this question, right? It's a little bit of a little bit more interpretation than I think necessarily it was intended for. That it was intended for. Let me see if I have anything on this here. I have some pages here with some of the answers printed out. Let me see if I can't find it. Okay, let me see. High blood pressure. This one's this one. Smoker. Yep, that's not that. Not that page. Not that page. Just hang on with me just a second longer, and I'll figure this out. Let's see if that's number 7. That's number 7. I don't think I have that. No, 58% may not be. Oh, I see what they're saying here. Okay. Is it likely to observe such a sample if, in fact, 58% of the Americans have said life? Well, no, it isn't likely. I mean, look at it from another perspective. It isn't likely because we would expect 58 if 58% of the Americans have a sedentary lifestyle. If we took 12 people, we would expect like 6 or 7 of them to have a sedentary lifestyle, not just not necessarily 10, right? So I guess you could argue it that way. Okay, all right. Okay, so it was unlikely. We agree that it was unlikely that we would get that outcome because we would expect if in fact we got a sample and 10 out of 12, 10 people were sedentary, then that doesn't look like the right percentage to us. Okay, now, okay, so the only other thing I want to mention is, and I'm not even sure that this is open territory for the test. I'm going to leave the page here. Is that sometimes you can have a situation where you're working with binomial distribution, but but it may be described in a way that you can look at it as a form of normal distribution. Again, pen back. Okay, so for instance, let's say we're dealing with coin tosses, right? So coin toss, if I were to say I'm going to toss a coin 100 times, right? I would expect to get 50% of those heads and 50% of them tails because the probability of heads is going to be 0.5, right? Probability of this outcome is 0.5. So if I were to do this over, and remember that Galton machine, where it could go either direction, but it's usually 50-50, like just flipping coins and stuff. I would expect that if I were to do this many, many, many times, and then graph the outcome for all of these trials, I would get most of them being in the middle here, about 50 heads when I toss a coin 100 times. I would occasionally get, like 45 heads, or I might occasionally get 45 heads, or 55 heads, and so on and so forth. And going out, maybe 50 heads, but not 40 heads, but not very frequently. Further out I go here, the less likely I'll get this outcome from my binomial output. So now I could actually describe this experiment, this coin toss experiment, as being kind of a normal distribution. Half the time I'm going to be above 50 heads, half the time I'm going to be below 50 heads. Well, in this case, I can approximate the nature of this distribution by saying the mean for this distribution is going to be equal to n times p. P is the probability of getting that outcome, which is 50%. 100 times 50%, in this case it's 50. I can also approximate the standard deviation of this binomial distribution by saying it's equal to the square root of n times p times not heads, 1 minus p, right? And that's going to be equal to the square root of 100 times 0.5 times 0.5. 1 minus p is 0.5. This is 0.25 times 100 is 25. The square root of 25 is 5, so the standard deviation is 5. So with a mean of 50 and a standard deviation of 5, you can then use this normal approximation for trying to figure out what's the probability of flipping a coin 57 times, 100 times, and getting 57 or more heads, right? You do the same thing you would do with your normal distribution, your normal tables, Excel, and so on and so forth. And you could calculate this probability using this normal approximation to the binomial distribution. If it comes up, you have a way of looking at this. If it doesn't come up, forget I ever mentioned this. Okay? So it's interesting. All you need to remember is these two formulas here. And you can apply it to any binomial distribution. Let's say I told you that you were taking a sample of 1,000 people at a time, and the prevalence of diabetes in that population was 0.1. Well, what would your mean what would your mean outcome be for this? It would be n times p, which would be 10% times 1,000 would be 100, would be the mean. And in this distribution, what would be your standard deviation? Well, it would be 1,000, right, times 0.1 times 0.9, and then the square root of that whole thing. And that's 0.09 times 1,000, 2, which is 90. Square root of 90 is approximately, let's say 9, right? So the standard deviation there would be approximately 9, right? And you could look at this as a normal distribution and do your calculations from that point.